Hi friends, welcome back. This is Santosh Kumar. So today we'll see the very important concept, that is the gain margin and phase margin. As per the GATE exam, this concept is very important. Already I have told you, wait a minute. The important concepts are what you will get. You will get the magnitude plot, and they will ask to find out the transfer function. According to me, what I have seen is 60% weightage to this for the GATE. Okay, means this one is very important. That's why I'm showing you. And the next one is these two things, that is gain margin and phase margin. Very important topic for this particular body plot. Okay, so let's take it 35% weightage to this. Okay, so today we are going to start the gain margin and phase margin. Till now we completed how to find out the transfer function if the magnitude plot is given to you. Okay friends, now let's come to the today's class, and that is we'll see first classification of the systems. The system based on what? The finite poles and zeros. Okay, the system based on finite poles and zeros are classified in three ways. I think you heard this all names. The first one is minimum phase system. But before that, let me talk about, see friends, this is the S-plane we are talking about, or we are doing our study in the all this whatever we are doing. Wait a minute. Wait. So this is the S-plane I'm taking over here. So whatever study we are doing, we are taking all the parameters in the S domain only, isn't it? How to find out the system stability? When the system will be stable, when all poles and zeros will be in RHS. No, this is LHS, isn't it? Left hand side of the S plane means the left hand side of the imaginary axis. If you have poles and zeros, your system will be stable system. If you have the poles in the RHS, your system will be unstable system, isn't it? If you have your poles over the imaginary axis, this belongs to the marginally stability category. So this classification is based on this finite poles and zeros location. Okay, so what I'm saying is, suppose, see, if your system is like this, in which your poles and zeros are in the LHS of the S-plane. Okay, when you will calculate the phase of this, let's take this phi 1. You have some poles and zeros in the RHS of the S-plane. You are finding out the phase of this phi 2, and somewhere your system is like, wait a minute, whose poles and zeros are like this. If this side is pole, this side is zeros. If here it's zeros, then these are the poles, kind of this kind of thing. Okay, means for the pole, single pole placed into the LHS of the S-plane, corresponding to this we have one 0 in the RHS. If one pole is seated in the RHS, corresponding to this pole we have 0 in the LHS. Okay, so this type of system, suppose, and in this system you are calculating phi 3. So three system I introduce over here. The first one is in which all poles and zeros are in LHS. The first, this is the very first one, your first system which have your poles and zeros in the LHS, and I calculated the angle phi 1. The second case, your system's poles and zeros are in the RHS, and I calculated the phase provided by that system, and I have given the name phi 2. The third one we are considering, and that is this type of system. If I have pole over here at -1, at +1 I'll have a 0. Or the second condition, if I have pole over here at +1, then definitely I'll have 1 0 at -1. This is the third type of system I'm talking about, and what I'm doing is I'm finding phi 3 for that. If you'll do like this phi 2, phi 3 and phi 1, they will be related like the phi 1 will be least phase among all. The phi 1 will be the least phase, or the system is nothing but the minimum phase system. Minimum phase system. Okay, when you will see the relation between all these three, what you will get is phi 1, then phi 3, then phi 2. This will be the relation for sure. You can check it. So this system, if your system belongs to this category, means in the LHS, means all poles and zeros are in the LHS of the S-plane. It will be minimum phase system. It will be minimum phase for sure. If your poles and zeros are in the RHS, they will provide non-minimum phase. Non-minimum phase we call it. And what about this phi 3? This phi 3 will be in between phi 1 and phi 2, and this type of system we call the all pass system. Okay, later we will discuss about this, don't worry. Okay, now let's come to the classification of the system. The classification system based on the finite poles and zeros in three ways. The first one is minimum phase system. So, as we discussed the minimum phase system, the poles and zeros of the system will be in the RHS of the S-plane. Isn't it? A system in which all the poles, the poles and zeros, and I'm talking about the finite poles and zeros, lie in the left of S-plane. Left of S-plane. The poles and zeros will be like this. Isn't it? So, the phase provided by the system will be least among all three, whatever we are looking for. That's why we are calling it the minimum phase system. Isn't it? Now, if I'll talk about the non-minimum phase system, a system in which one or more zeros or poles lie in the right of S-plane. Isn't it? Right of S-plane means, suppose over here you have zero or poles. Entirely for the entire system, you may have some poles in the LHS also for that. But definitely there is a condition for sure, you should be having one pole or zero in the RHS. This is must condition. Suppose in the system or in that system you have some poles and zeros. Some may have in the LHS, no problem at all. But there will be condition that some zeros and poles should be there in the RHS. It will be non-minimum phase, isn't it? So this is the right of S-plane I'm talking about. And if we'll see the all pass system, the condition for the all pass system, a system in which all zeros lie in the right of S-plane, if the condition is, I'm taking over here the S-plane. I'm sorry for this khatarnak diagram. So if you have zero over here, you will be having pole over here, and the reverse is also, true. What it means, see, a system in which, wait a minute, a system in which zeros lie in the right of S-plane and all poles to the left of S-plane, which are symmetrical above the imaginary axis. So this pairing will be symmetrical about the imaginary axis, and the reverse is also true, means you can change the positions of these two. Okay, so this is the all pass system. So the phase provided by, what I am saying is, let me take the pen over here. If the phase provided by the minimum phase system, practically will take this condition, or we'll get, while solving the problems, we'll get this problem, if minimum phase system is providing, suppose minus 90, and all pass system will always provide minus 180 degree. We'll see why. Non-minimum phase will be summation of this two. It will provide minus 270. Okay, so I am taking over here to the transfer function of non-minimum phase system. let me change the pen. Non-minimum phase system. I'm taking the transfer function. Okay, so let's make it. Can I do like this? S plus 1, S plus 3, S plus 5. The condition is there should be at least one 0 in the right of S plane, S minus 2. So this 0 will make it non-minimum phase system, else the system is minimum phase system. Okay. Now let's see. Can I write this like S plus 1, S plus 3, S plus 5, and what I'm going to do is I'm multiplying this by S plus 2, S plus 2 in the numerator and denominator. Can I write like this? So this is nothing but the all pass filter, isn't it? Or the all pass system. The all pass system condition is if you have 0 in the RHS, corresponding to that 0, the symmetric pole you will get in the RHS. So this is nothing but the all pass system, isn't it? What about this system? This system is entirely minimum phase system, isn't it? All poles and zeros are lying in the LHS. You can see LHS of S plane. So this is the MPS, isn't it? Now they are in multiplication, and suppose the phi, the angle provided by this is suppose phi MPS, minimum phase system, and because of this suppose phi is APS, and if two things are in multiplication, their phase we can add, isn't it? So I'm taking in the form of phase. This is the phase of non-minimum phase system. So this is nothing but phi of MPS plus phi of all pass systems, isn't it? This is the relation always in between all these three things, isn't it? So the phase provided by non-minimum phase system is nothing but the summation of phase provided by minimum phase system and all pass system. Okay friends, now if you have this curve, wait, so you have this, isn't it? Now I'm asking to you, which type of system characteristic is given? Minus 90, this will be minimum phase for sure. Minus 180, it will be all pass system. What about this? Non-minimum phase system 100%, isn't it? The condition is true always. You can add this 2, you'll get minus 270 degree. Okay, so in the negative, the phase provided by this system is maximum, isn't it? So this is all about the minimum phase system, all pass system, and non-minimum phase system. Now the most important thing is the stability condition. The stability condition we are going to discuss now. The stability condition, see friends, the stability condition are given by the characteristic equation always, isn't it? For any system we are dealing with the closed loop control system stability. So when we'll make the control system closed loop control system, will get the characteristic equation, isn't it? This is the the characteristic equation. Now if I'll take this in the frequency domain, so it will be j omega minus 1, isn't it? Now if I'll take the magnitude of this, it will be the magnitude you have to take. So the magnitude of minus 1 and j0, can I say? So this is nothing but the 1, isn't it? So this 1 in the linear scale we are talking about. Okay, I'll show you what is the linear scale. Now if suppose to this magnitude you will convert into the dB, what you have to do is you have to do the 20 log of this, isn't it? 20 log of j omega So your system magnitude will become in dB. Over here you will take 20 log 1. 20 log 1 is nothing but a 0. So in dB, your magnitude for the stable system is 0 dB, and in linear it should be 1, isn't it? Correct? So based on this concept, let's talk about, or wait a minute. So this is about the magnitude, but what about the phase? If you'll find out the phase of this system, so you'll get this one is minus 180 degree, isn't it? Or the odd multiple of this. The magnitude will be 1 in linear scale or 0 in the dB for the closed loop stable system I'm talking about. The two reference conditions we are generating over here, and with respect to these two conditions we'll proceed further. Okay, so the point is the phase should be minus 180 degree and the magnitude will be 1 in linear scale or 0 in dB. So now we are going to define the gain crossover frequency. If I am checking this is the the characteristic of the stable system I'm taking. This is the stable system, the root locus I can say, or the path projection of the roots. Okay, now here we are checking two things in consideration. All these things is for the gain margin and phase margin. Now I'm going to introduce the gain margin and phase margin, but before that let's understand the gain crossover frequency. The frequency at which the magnitude is 1 in linear scale and 0 in dB is called the gain crossover frequency. This is the plot. This is the plot plotted against the omega's value. Means at omega equal to 0 it will start at omega equal to infinity, and it will terminate at omega equal to 0. Later we'll discuss about this, don't worry. Okay, but for the understanding of the gain crossover frequency you have to remember this. This is the plot I'm talking about. The gain crossover frequency is the frequency at which the magnitude is 1 in the linear scale and 0 in the dB. Where is the magnitude? This is the unit circle I have drawn over here. This is the circle having radius 1. This is your path of your system roots. First time over here it's becoming 1, isn't it? It's crossing to the unit circle. So here the magnitude is 1. So in this case this frequency is nothing but omega GC. The frequency at which the magnitude is 1 in the linear and 0 in the dB is the by default condition. Definitely if the magnitude is 1 in the linear and you will convert into the dB, you will get the 0 dB, isn't it? So this is the frequency, we call it the omega GC. Now the next frequency is the phase crossover frequency. Now it says the frequency at which the phase angle is minus 180 degrees is called the PCF. Here is the minus 180 degrees, and this line is nothing but the indicating the minus 180 degree. So first time over here your plot is intersecting this line of the minus 180 degree. So this frequency corresponding to this point is nothing but phase crossover frequency, isn't it? Is it okay to you? So we have seen two things, the gain crossover frequency and the phase crossover frequency. Now we'll see the very important thing, and that is the gain margin and phase margin. So come to the gain margin. So mathematically the gain margin is given the reciprocal of the magnitude at omega PCF. At the phase crossover frequency, the reciprocal of the magnitude is nothing but the gain margin mathematically. The gain margin is defined, let me take over here the highlighter. The gain margin is defined as a reciprocal of magnitude of system at omega PCF. This point is very important. Magnitude at omega PCF. Where is the omega PCF we have seen? Here is the omega PCF, isn't it? So at the omega PCF, the phase crossover frequency, the frequency where your plot is cutting to the minus 180 degree, isn't it? So over here, whatever will be the magnitude, you will take the reciprocal of that magnitude, and that will be your gain margin, isn't it? So this is the mathematical, but what is the implication, or what is the physical definition? See, it is the factor by which the system gain increases to drive the system to the verge of instability. Means the gain margin is giving the idea of, wait a minute, so we are talking about the physical implication of this. So this is giving the idea whether your system is stable, or at what time your system will be, tends to instability or verge to instability. So gain margin is giving the idea. See, wait a minute, suppose let's take at this point at omega PCF, yes, no problem. What you are getting, you are taking suppose 0.5, the 0.5, isn't it? Now the gain margin is nothing but the reciprocal of this, and the reciprocal of 0.5 is 2. So what this 2 is going to indicate, the factor by which if your system will multiply it. Now if you will multiply this system, this point will come to 1. This point will come to 1, your system will, and after this 1 your system will become unstable. According to this, we'll discuss about this graph also, how this came. But for the time being, you have to know that if your system will reach out of this, it will become an unstable system. In this, it will be a stable system. At this exact point, it will be marginally stable system. So gain margin is giving the idea whether the system is stable and when it will go to the instability, isn't it? So friends, in today's class will be limited to gain margin only. In the next class we'll discuss about the phase margin, and we'll see some problem based on gain margin and the phase margin. If you have still some doubts, we'll clear in the next class. Okay, so we'll meet in the next class. Till then, take care and bye.